So now what we will be doing is, in the previous sessions, 4 video lectures, I have given the notes also as well as the recording also. In that, what we have seen is kernel of the homomorphism for rings, analogous to kernel of the homomorphism for groups, the same thing. Then there we proved under the group structures that kernel is singleton 0 in case if it is a 1-1 mapping. The similar sort of proof we did under rings also. Second thing. Then there we have proved the fundamental theorem of homomorphism. The similar sort we did here also, fundamental theorem of homomorphism. So till that I have shared. Now we will be learning about a new concept, that is maximal ideal and prime ideals. We will be learning about 2 different types of ideals. One of them is maximal ideal and the other one is a prime ideal. So first let us see what do we mean by a maximal ideal. Let's have a look. Now we know that a set of integers is a ring. So now let us consider what is set of integers. Our set of integers is the ideal generated by element 1, we can say here in this case. And then coming to the next one, let us consider an ideal generated by all multiples of 2, let us see. An ideal generated by all multiples of 4, let us see. Now, what is this ideal generated by 2? It consists of all the elements, say, suppose -4, -2, 0, 2, and then 4, etc. So on, we will be having. Then what is this ideal generated by 4? Here, this consists of -4 and then 0 and then 4 and then 8, etc. So on. Now, if we see, this set is a subset of this particular set. So now, ideal generated by 4 is a subset of ideal generated by 2, we can say. So this set, ideal generated by 4, is inside or contained in this particular ideal. But whereas when I consider ideal generated by 2, there is no ideal in between ideal generated by 2 and ideal generated by 1. So what we say is this ideal generated by 1, we call it as the ring, and the ideal generated by 2, we call it as a maximal ideal. Now, what is the maximal ideal is the question. When do we say an ideal is the maximal ideal is if it itself is the biggest ideal contained in the ring. What do we mean by saying the biggest ideal is the question? Means there shouldn't be any other ideal which is larger than that one. So how do we define it? A maximal ideal M of a ring R is an ideal. It is different from R such that there is no proper ideal U of R properly containing R, or else the other way, how do we define this is, say suppose R is a ring and M is an ideal of R, so that M is different from R. When do we say this M as a maximal ideal of R is in case if there is an ideal U in of R in such a way that M is a subset of U is a subset of R, then either our R is U or our U is M. That means there shouldn't be any ideal of this form U in between M and R if M is the maximal ideal. Okay. So M always will be a maximal ideal if any ideal U of R containing M is existing, then that ideal must be either your U must be equal to M or your U must be equal to R. And then in another way, putting in another way, an ideal M of a ring R is called maximal ideal if M is not included in any other proper ideal of R except itself. So, the only ideal containing M should be the ring R itself. In such cases, we call M as the maximal ideal. Now, let us see the example. R as the set of ring of integers. Consider U1 as ideal generated by 2, U2 as ideal generated by 4. So, U1 is 2Z, U2 is 4Z, we say. Now, we know that 4Z is a subset of 2Z, which is a subset of our ring of integers. So, I cannot say 4Z as maximal ideal, but I can say 2Z as the maximal ideal. In the same way, say, consider ideal generated by 3Z, ideal generated by, say, 9Z. 9Z is a subset of 3Z. So, I can't call 9Z as maximal ideal, whereas 3Z is the maximal ideal, we can say. So now let's have a look at a theorem with regard to the maximal ideals. What does this theorem state is, in the ring of integers, the ideal generated by prime integer is always a maximal integer, maximal ideal. So ideal generated by prime integer always becomes a maximal ideal. So now let us check, is it so or not? So let M be an ideal of Z generated by a prime integer. What is prime integer? It has only factors, the number and it itself. So let us assume that M is generated by P, where P is a prime number. So now let us show that this M is maximal ideal. What do we mean by maximal ideal? If there is any other ideal U, then either M should be or your U should be equal to R. So let us assume that U is an ideal of Z in such a way that M is a subset of U is a subset of Z. So what we know about set of ring of integers is, the ring of integers is a principal ideal ring. Principal ideal ring means what? Every ideal of the ring is a principal ideal. What do we mean by saying principal ideal? It means every element of the ideal is generated by one single element. Example, ideal generated by 2. What are the elements? 2, 4, 6, 8, etc. So on, all multiples of 2. Ideal generated by 5. 5, 10, 15 or minus 10, minus 15, etc. All elements of the ideal are multiples of 5. So if it is a principal ideal, it should be generated by one particular element. And every ideal of ring of integers is a principal ideal. So U must be a principal ideal. Means it should be generated by some Q. So where Q is an integer. Now what do we have? We have M is a subset of U is a subset of Z. But so what does that mean? M is ideal generated by P. U means ideal generated by Q. And Z means ideal generated by 1. So, ideal generated by P is a subset of ideal generated by Q, we are saying. When does that happen? P is an element of Q. Means P belongs to ideal generated by Q. What is this? What are the elements of this particular set or ideal? All multiples of Q. So, your P must be a multiple of Q. Means I can write P as Q into M. Since P is a prime number, what are the possible options we have? We have only two options. What are they? These two numbers. Either Q should be 1 or m should be 1. So q should be 1 or m should be 1. What will happen if m is 1? If m is 1, your p is equal to q. Then ideal generated by p is ideal generated by q. Then your m must be equal to u in that case. Say what happens if q is equal to 1? Then ideal generated by q is ideal generated by 1. But what is that? That is nothing but the ring of integers z it itself. So that means your u is nothing but z. So in case if we have an ideal u like this, we are having either m is equal to u or u is equal to z in this case. That means there is no proper ideal of z containing your ideal m. That means m is the maximal ideal, we can say in this case. So here, in case if an ideal is generated by a prime integer, always it should be a maximal ideal. Now, what is the other conclusion you can draw here? If it is generated by prime number, it should be maximal. If it is not generated by prime number, it should be a composite number, you can say. So in case if it is a composite number, can the ideal become a maximal ideal? Never. Example, let us see. Ideal generated by 6. 6 has two factors, 2 into 3. So ideal generated by 6 is a subset of 2. So what can I say? This can never be a maximal ideal. In the same way, ideal generated by 6 is a subset of ideal generated by 3. So this can't be a maximal ideal. Say for example, another example, let us take ideal generated by, say, take another composite number. Say suppose, let us take, say 12. What are the factors of 12? We have 2 into 6, I can write 12 as, or else 3 into 4, I can write 12 as. So what can I say? Now, ideal generated by 12, it can be a subset of ideal generated by 2, or can be a subset of, it is a subset of ideal generated by 3, and it is a subset of ideal generated by 4. It is a subset of ideal generated by 6. So how many ideals are there? There are 4 ideals consisting of the ideal 12. So this can't be a maximal ideal. Can this be a maximal ideal? No, this can't be. Can this be a maximal ideal? This can't be. Now, can this be a maximal ideal? Yes, this can be a maximal ideal. Reason, this is the prime number. This can be a maximal ideal. Reason, again, this is a prime number. So, in case if the ideal is generated by a prime number, then what we can say is always it becomes a maximal ideal. Now comes the question, what will happen to the converse of this particular theorem? So if it is a maximal ideal, can you say that it is generated by a prime integer or not? Let us check that. If m is a maximal ideal, then m should be generated by a prime integer, says the next theorem. Let's have a look at the proof. Let m be a maximal ideal of z. Maximal ideal, we are saying. Ideal means it should be generated by some element. Take the element as n, where n belongs to z. So we need to show that n is prime number. On the contrary, assume n is not a prime number. Then it should be a composite number. Composite number means it should be written as product of two integers. So let us write n as product of two integers a and b, where a and b are prime numbers. What does fundamental theorem of arithmetic says? Every integer you take, it can be expressed as product of prime factors. In your school level, you learnt about this fundamental theorem of arithmetic. So we make use of that. So as n is an integer, it can be written as product of two prime factors, a and b here in this particular case, where both a and b are prime. So now let's consider an ideal. A is an integer, b is an integer. So we can have an ideal generated by a, have an ideal generated by b also. So let u is equal to ideal generated by a. Now, as n is ab, what we can say is m is a subset of u and u is a subset of r. But m is maximal. So either you should have m is u or u is r, we must have. What will happen if m is equal to u, or what will happen if your u is equal to z? Let us check. Say if u is equal to z, then what is our u? We are saying u is ideal generated by a. What is your z ideal generated by the unity element? That is 1. So ideal generated by a is equal to ideal generated by 1. When will it happen? Provided a should be equal to 1. Then your n is AB, we are saying, means n is equal to B. So that means your n is a prime number in this case. Now, what is the other case? In the second case, we have let m is equal to u. Then ideal generated by a is equal to m. But what is m? Ideal generated by n. So we are saying ideal generated by a and ideal generated by n are same. Means your a should be an element of m. Means, Aparna, mute yourself. So your a belongs to ideal generated by n. What are the elements of ideal generated by n? All multiples of n. 1, 2, and 3, and 4, and 5, and like that. So your a should be some Rn, for R belongs to Z. Then your n is equal to AB. But how can I write your A? I can write it as Rn into B. So this is commutative ring. So Rn can be written as Nr into B. So n is equal to n into Rb. Cancellation law apply. N and n I can cancel. So 1 is equal to Rb. Product of two integers is 1, we are saying. When would it happen? Only it should be 1 into 1 is the only option we have. So your R must be 1. Your B also must be 1. So your n is a into 1, which is a here in this case. Then what does that mean? Your ideal generated by m, n is, that is m is equal to u. Now u is, a is this ideal generated by, a is our u, and this a is a prime number. So n becomes a prime number here. So thus n must be a prime integer, we can say. So whenever you have a ideal generated by a composite number, it can never be a maximal ideal. So when it can be a maximal ideal? Provided it should be generated by a prime number, that is generated by 2, 3, 5, 7, 11, etc., etc., all those things. Now, both these two theorems putting together, we can state as one particular theorem. What is that? An ideal in Z is a maximal ideal if and only if it is generated by a prime integer, we can say. Now, so this is with regard to the maximal ideal. Now, we have another important theorem on maximal ideals. What is that is, when this, what is the property of this maximal ideal is, when this M becomes a maximal ideal is the question. When does M become a maximal ideal is of a ring R is provided R by M always should become a field. In case if it is a field, then only your M becomes a maximal ideal, we can say here. So the next theorem is one of the important and repeated theorems. What does that theorem state is? M is a maximal ideal of a ring R if and only if R by M is a field, is the statement of the theorem. What do you mean by field? It should be a commutative ring. It should have unity. Apart from that, what else it must have? It must have, every element in this set must have a multiplicative inverse. So what we need to establish is, whenever there is an A plus M belongs to R by M. What are the elements of R by M? All cosets. What are those cosets? All A plus M form. So what is this A plus M? The set of all A plus small m, where your small m belongs to capital M is the coset. Now take any element from this set, say A plus M. What we need to exhibit is, there exists a B plus M in R by M, such that your A plus M into B plus M is equal to 1 plus M, we can say here. So you need to exhibit every element. This is an if and only if condition. M maximal means R by M is a field. R by M field means M is maximal, we can say here. So that's it. I'll end because this session lasts only for 40 minutes. We can't extend. So if you all join tomorrow also, we can see the proof of this particular theorem tomorrow. So now, 1 second, can I have all the videos turn on, please? Be quick. And then who is this roll number 5? I can't recall. This fellow is sleeping. Dadas? Just right. Okay. That's all for today. Good night. And tomorrow evening we'll join at 6 p.m. Okay?
Good night.